Okay, so now we have proven part 1 of proposition 1.3.10, which tells us that we can uniquely extend additive functions in an additive way from semi-algebras to algebras of sets. Now we're going to prove part 2, which is that if you have countable additivity, then that gets preserved as you do this extension. So here's the full setup. Proof of part 2. Assume S is a semi-algebra of sets on X, and let A be the algebra of sets that S generates. We now know that A is simply finite unions of things in S. Now let mu be an additive function on S, and let mu bar be its additive extension. I can now use phrases like that, right? Thanks to part 1 that we already proved, I can say let mu bar be its additive extension. There's a unique one. So now to prove part 2, I should actually assume mu is countably additive. I guess I could have written it up here, let mu be countably additive. But whatever, I'm writing it down here. So assume mu is countably additive. Now the goal is to prove mu bar is countably additive. If we do that, by the way, then mu bar will technically be a measure, right? If we prove mu bar is countably additive, then mu bar will be a measure on X along with this, which this is not a sigma algebra, it's only an algebra as far as we know here, but that's, we do still talk about things as being measures when you have a countably additive function on an algebra of sets. So the conclusion that we want in part 2 is we want to prove that mu bar is a measure. Okay, so we want countable additivity for mu bar. So let an be a sequence of sets in fancy A, and let's say pairwise disjoint. Sequence of disjoint sets in A. And and assume this, we have to assume that their union is also in A. Let's give this union a nice name. Let's call it just plain A with no subscript. So assume that that's also in fancy A, and this has to be an assumption, right? Fancy A is only, as far as we know, an algebra of sets, not necessarily a sigma algebra. Then we want to prove that mu bar of this union is the sum or infinite series of the mu bar of the ANs. Somehow this is supposed to follow from the countable additivity of mu. Mu, whose domain is only the semi-algebra. So there's no hope of getting anywhere without breaking down these ANs in terms of unions of things in the semi-algebra. So for each n, we can write A sub n, since A sub n is going to be an element of fancy A is the union of, is a set of finite unions of things in fancy S. And in fact, it's also the set of finite disjoint unions of things in fancy S, again, using good old part 2 of lemma 1.2.14, that you can always ensure these are disjoint. So we can write an as, let's say, the union, so it'll be a finite union of some s's. So how do I denote this? Sn I, this n is this n, and I is the index for the union. So from I equals 1 up to some number that depends on n. It could be a different number for each n there. Okay, so we can do this for some Sn1 up through Snn. It's a little awkward, in, at least reading it out loud, in fancy S. Pairwise disjoint. So it can be arranged that these S's are pairwise disjoint, thanks to that lemma. Now we can actually say what is mu bar of A, right? Or, no, I'm sorry. Yeah, okay, this is confusing. Actually, we cannot say, we don't have enough notation yet to write down what is mu bar of A. Since I was about to go down this wrong path, let me show you it, since it's interesting that it doesn't work. You might think, oh, well, we've written A as a union of things, and each of those things is a union of things, so mu bar of A is mu bar of this union of this union, right? So then it should be a sum of mu bar of the SNIs, which is mu of the SNIs. Nope, sorry. Mu bar is additive. We are actually trying to prove it's countably additive. So we do not have, this kind of decomposition is not sufficient for us to say what is mu bar of A. Nope. There is such a thing as mu bar of A, but it's not, this is not what it is by definition at least. This is what we'd like to prove it is. There is such a thing as mu bar of A. We know that for sure because we have assumed, here's my pointer, here, we have assumed that A is in there. And that means we have assumed A can be written as a finite union of things in S. But this way of writing it is not a finite union of things in S. So this is not a way of writing it as a finite union of things in S, but it can be written as a finite union of things in S. All right, but what we do know about at this stage is what is mu bar of the ANs. Right, so let's just say it so that we have it. Then mu bar of AN is going to be the sum from I equals 1 to n sub n of mu of the SNIs, right? Or mu bar or mu of the SNIs. I can say mu here since these are in S. Okay, so this is like, you can say this is using the definition of mu bar, or using the additivity of mu bar and the fact that mu bar extends mu. Okay, but our goal is to say something about mu bar of A, right? We're trying to prove countable additivity. We want to say something about mu bar of this thing. So how do we say anything about that? We need to use the fact that this is in A. So since A is in there, we can write this as a union of finitely many things in S. And again, thanks to this lemma, part 2, we can write it as a union of finitely many disjoint things in S. So there are, what should I call them? Should I call them S's? I'm going to follow the textbook's convention so you can compare things if you want to some extent. There are, let's call them BJs. So B1 through Bm in S, pairwise disjoint, such that A is the union of the, let's call them BJs. Now in this context I can say what is mu bar of A, right? It's the sum from j equals 1 to m of mu of the BJs. Okay, so it seems that my goal is to show that the series of these, right, like the sum over all natural numbers n of these is equal to this, right? That's the goal with countable additivity. So my goal is to show that the sum over all little n of these is equal to this sum. It's kind of a weird thing to have to show. I don't know, maybe not that weird. I just didn't expect to be doing it quite like this. So here we can benefit from doing a kind of common refinement kind of trick like we did in the previous video. So each of the b's, let's see, so there are these finitely many b's that union up to give A, right? And each b, like last time, let's just focus on one of them, like B1, and then generalize the idea. So B1 is going to be definitely a subset of A, right? Since the union of b1 through bn is A. So then b1 is b1 intersect A. Let me do it in this kind of set algebra way, which is b1 intersect, and then A is the union of the ANs. And so distributing that intersection over the union, b1 is the union of the b1 intersect ANs. But each AN is going to be, let's make some room, each AN is a union, where did it go? Each AN is a union of S's, right? SNI's. Each AN is a union of SNI's. So this is a union and then B1 intersect, and then this union of SNI's, right? But then let me just distribute that intersection over the union. So let me just skip that step quickly. So each AN is this union of SNI's running from I equals 1 to I equals big N sub little n. Okay, now just to cut down on the number of index variables, I was looking at B1, but let's, instead of B1, focus on Bj for any j. So this works for any of the b's. And now we have these interesting triple indexed things. So let's call this C Nij. So I've got these sets C Nij, where n is allowed to run over all natural numbers, then I is allowed to run over some finite range depending on what n is, and j is always running from 1 to m. So I've got this family of sets. Interesting. So remember, the goal here is to kind of get a common refinement of two partitions. And I'm deliberately using the language that we used when we were looking at partitions for the sake of Riemann integration. Of course, here when I say partition, it means something a little different. Back then, partition was a finite collection of points in an interval. Here, partition literally means like a set theoretic partition. So a way of writing a set as a union of disjoint sets. But it's nice that the same language, the same words literally work. Okay, so the reason I'm scrolling back up is to remind myself what are the two partitions that I'm trying to commonly refine. So I've got this, I've got A partitioned on the one hand into the B's, and here I've further subdivided the B's into these CNIJs, so the B is subdivided into the C's. And then I have another kind of partition of A, which is A is a union of the ANs, and the ANs are unions of S's. So I've got a partition of A into S's. So now my goal is to further subdivide the S's into C's. So here's the schematic in my head, kind of. I've got A. On the one hand, I have it subdivided into B's, and on the other hand, I have it subdivided into S's by first subdividing it into A's, ANs, and then S's. And then I'm going to try to subdivide both of these into C's. That's the idea. So I've done this, now I'm going to do this, subdividing the S's into C's. So for each n, okay, this time I'm not going to fix one of the indices at 1. I guess there's not really any reason to do that. It's not that hard to process a lot of indices. It's not that hard to process one more index, right, mentally. So for any n in there, that doesn't make any sense. What am I doing? For any natural number n, and for I, in there. Let's focus on subdividing S sub ni into C's. So we know that the S sub ni's are contained in A sub n, because they are, their union overall I is going to be A sub n. So they're contained in A, which is the union of the B's. So then, S sub ni equals S sub ni intersect A equals S sub ni intersect this union of the B's, which is, if I distribute this intersection, let me write it as a union from j equals 1 to m of S sub ni intersect bj. And hey, that's our thing that we called Cnij. So there, I have further subdivided the s's into c's. Now I'm done sort of working out my common refinement thing, the C's. In order to ensure that the C's can be used when I evaluate mu bar, the extended mu, on things, I don't know why I'm scrolling around while I'm talking. Sorry. In order to make sure that it works to evaluate mu bar on various things that I'm going to write as unions of C's, it will be important to know that the C's are in S and that they are disjoint. So the Cnij's are in S. Is that clear? Yeah, they're just intersections of things in S, and a semialgebra is closed under intersections, right? The B's and the S's are in S. That was the whole point. The B's are in S, and the S's are in S. Okay, now for something that's a little bit harder to think about, mainly just because of how many indices are floating around right now. The Cnij's are pairwise disjoint. Okay, I think this is worth writing carefully instead of trying to hand wave through it. So to show that an indexed family of sets is pairwise disjoint, you should assume that you have two, let's say Cnij, two sets with non-empty intersection, and then see if you can prove the indices are equal. So Cnij, let's say, meets the set Cn prime, I prime, j prime. So let's say this intersection is non-empty. So now the goal is to prove that n equals n prime, I equals I prime, and j equals j prime. Okay, well let's first think about, I think j is easy to work out. If j didn't equal j prime, if j and j prime were different, then we'd have a certain subset of, so remember the j's show up here. This is the definition of Cnij. The j's show up here. If you had two of these C's with different j index values, which had a common element, then you would have two, one subset of one of the bj's and one subset of a different bj having a common element, which cannot happen because the b's are assumed to be pairwise disjoint. So remember, the b's are assumed to be pairwise disjoint, and each individual family of s's, so like if you fix n, then Sn1 up through Sn and n, those are assumed to be pairwise disjoint. Okay. So since the bj, since this family running over all j in 1 through m is pairwise disjoint, we must have j equals j prime. I don't think it makes sense to say the word the if I'm going to write it as an indexed family like that. Okay, now what about the n and I? So could n be different from n prime? So I'm going to say that since this original sequence of things that we started with, the ANs, is pairwise disjoint, we must have n equals n prime. So think about it. If you had, so now we know that j and j prime are the same, right? Now suppose you had, actually it doesn't even matter, these are independent questions. Suppose you had something in a Cn ij and something in, and that same thing in Cn prime I prime j prime. And suppose n and n prime are different. Then you have something in here and in another one of these, but with the n changed, right? Then that would be a common element. Remember, we assumed that the ANs up here are disjoint. So that would be a common element to one AN and a different AN prime. That would violate the disjointness of the ANs. And then finally, since, so now we know that, now it's worth restating what we have, but using what we know. Now we have Cnij intersect Cn, n prime equals n, I prime, and then j equals j prime. So then finally, since the Sn i's running over I and there, since this is a pairwise disjoint collection, I equals I prime. Okay, great. So let's contain that stupid little argument there. The C's are pairwise disjoint. So now let me go back. I've got my decomposition of B's in terms of C's. So I'm going to use this. And I've got my decomposition of S's in terms of C's. So I'm going to use that. And I'll be able to write down what is mu bar for these. So what is mu bar Bj? And what is mu bar Sni? Okay, so let me do this off screen. I'm just going to copy over what Bj and Sni are from up there. Okay, there we are. So Bj was this in terms of the Cnij's, and Sni was this. And now we know, now we can finally use the, sorry, this should still be mu bar, but now we can finally use the definition of mu bar on this. So we're still not using countable additivity. These are finite unions, but I'm using, I guess I could say the definition of mu bar. Mu bar is the additive extension of mu. So it's, yeah, I guess I'm using the additivity of mu bar. So here's a finite union of disjoint things in S. That's why it was important to know that these are disjoint and in S, so that I can now do this. Wait, hang on, this is not a finite union. Okay, let me do this one first. So this is the additivity of mu bar. And these are in S, right? So I can just write mu. The C's are in S in the semi-algebra. So I can just write mu. And then here, right. I can actually write just plain mu here, because this is one of the B's. The B's are in the semi-algebra. So as complicated as this looks, it's in the semi-algebra. And so are the C's. So, okay, so this is the exact kind of situation where you can use countable additivity of mu. That's our major hypothesis, right? We're trying to prove this proposition here. We're trying to prove that if mu is countably additive, then mu bar is. So this is where we finally get to use the countable additivity of mu. It tells us that if we have a countable collection of pairwise disjoint, which we checked, the C's are pairwise disjoint, things in the semialgebra whose union, even though it is infinite, somehow ends up still being in the semialgebra, which this B is, then we have this. And this is now an infinite series. So part of the countable additivity of mu is the fact that this series converges. If you want, you can view it as applying countable additivity of mu to push the mu to this position, and then applying additivity to push it to this position. We can view it that way since actually even these portions are also in the semialgebra. These are the S's, S sub ni. Okay, we're almost done here. So now mu bar of A, that's what this was all about, right? It was all about mu bar of A. I cannot write it in terms of mu bar of the ANs, since that was an infinite union, A as the ANs, but I can write it in terms of these. So I wrote this before, but I'm just writing it again. This is, by additivity of mu bar, this is what mu bar of A is. Okay, and now we've written out these, so this is let me just copy this. So now this is a sum of series, right? So this is like a finite sum of series here. A finite sum of infinite series, all of which converge. For all j, this is a convergent infinite series. So from sort of the algebraic series theorem, or whatever we called it, we can do this. And initially I'm pushing this in, but let me push it in further actually, past the other finite sum. No calculus involved there, that's just rearranging finite sums. There. And now I've written it so that you see this here, right? That's mu bar Sn Sni. So this is mu bar Sni. Okay, now we're getting somewhere. So, oh yeah, we're almost there. So this, the sum of the mu bar Sni's, we pointed this out before. This is what mu bar of An is, right? And actually, I'm allowed to write mu there. I don't know why I didn't. It doesn't really matter, but I'd rather write mu when I can. So this is mu bar. Now I have to write mu bar here of the, so here I can write mu. Here I have to write mu bar of the ANs. All right, and look at that. That's countable additivity of mu bar right there. Here. This equals this. That's countable additivity of mu bar. Oof. All right. So now we've got this really nice, powerful proposition. So to summarize basically all of today's lecture, we can now go from like semi-algebra to algebra by just taking finite unions. And we're also saying we can take additive function on semi-algebra to additive function on algebra. So we're sort of carrying the package. An S with a mu goes to an A with a mu bar. And if it's countably additive, then it becomes an actual measure here, countably additive here. It'd be nice if we can go to sigma algebra, right? If we can go ahead and close this under countable unions as well. But we know that's a lot more theoretically involved, right? It's really hard to describe what is the sigma algebra here. It's not just like the transition from here to here is very constructive, right? You can just say things in here are unions of things in there. But from here to sigma algebra, that's going to be difficult, as we have seen. So more theory is needed, and that's what we're focusing on next. And hopefully we can also carry over our additive functions along to sigma algebras.